Hi, welcome to one and all. Next, we will be discussing about separability property of Gauss sum. Before we go to the separable functions, Gauss sum, separability of Gauss sum, we will be looking into the previous theorem which we have discussed. That is, if chi is any Dirichlet character mod k, then g of n chi is equal to chi bar of n g1 chi. This happens only, that is the Gauss sum is equal to chi bar of n times g of 1 chi only happens when GCD of nk is 1. So this is what separable Gauss sum means. That is, the Gauss sum g of n chi is said to be separable if g of n chi is equal to chi bar of n g of 1 chi. So that is, by the previous theorem, it means that this g of n chi is separable whenever n is relatively prime to GCD of n and k are n and k is 1. That is, n is relatively prime to the modulus k. So let us see the theorem. If chi is a character mod k, the Gauss sum g and chi is separable for every n if and only if g of n chi equal to 0 whenever n chi greater than nk, GCD of nk is greater than 1. So this is an important result because earlier we have studied that g of n chi is equal to x chi bar of n g of 1 chi. Then this theorem states what happens in the case nk, GCD of nk is greater than 1. That is what the theorem says. So in that case g of nk is 0. That is what it happens. So for the necessary condition is that we have not said anything about g of n chi in case of nk greater than 1, because this happens only when GCD of nk is equal to 1. So in the other cases also, if Gauss sum is separable, then g of n chi is 0 in all the other cases. That is, GCD of nk is greater than 1. So this is what we have to prove. But the proof is quite simple, because the separability always holds if GCD of nk is 1. That we all know, that we have studied in the previous theorem. But if GCD of nk is greater than 1, what is, by definition of the Dirichlet character, we can see that by what is the definition of Dirichlet character? If this chi of n is 0, if GCD of nk is greater than 1. So this is 0. That means a chi bar of n is also 0. So what is our theorem? So by our theorem, if GCD of nk is greater than 1, we have chi bar of n is 0. So from the definition of separability, we have this definition of separability. We have this g of n chi is 0, or nx, it is n chi is 0. So in all cases when GCD of nk is greater than 1, we have n chi is 0. This is n chi, not nx. G of n chi is 0. Hope you understood this theorem. Now we will go to another theorem on the separability. The Gauss sum, if g of n chi is separable for every n, then absolute value of g of 1 chi whole square is k. This is what we have to prove. So just straight away theorem, let us see what happens. So g of 1 chi, absolute value of g of 1 chi square is nothing but g of 1 chi times g of 1 chi bar, which is because of the modulus property of this number. This is a complex number, complex function, so we can apply this. So by the definition of this g of 1 chi, what is g of 1 chi? It is sigma m equal to 1 to k chi m e raised to 2 pi I m by k. So the conjugate of this, what is the conjugate of this? This is g of 1 chi times sigma m equal to 1 to k chi bar of m e raised to minus, the conjugate of this raised to 2 pi I m by k is e raised to minus 2 pi I m by k. Now here this we are taking this g of 1 chi times this chi bar m. What is this? Again, this is nothing but g of m chi by the separability. So this is g of m chi e raised to minus 2 pi I m by k. Now again we will apply the definition of g of m chi, that is nothing but sigma r equal to 1 to k chi of r is 2 pi I m r by k e raised to minus 2 pi I m by k. So this summation we are switching over. We can taking this summation r equal to 1 to k outside and chi of r also outside. The remaining terms we are taking together. Sigma m equal to 1 to k e raised to 2 pi I m r minus 1. So here we are taking 2 pi I m outside. So r minus 1 will come by k. Now this we already know, this is a geometric sum. So the sum will reduce to 1. This sum will reduce to 1 when this k divides r minus 1. So this happens only in other cases the sum is 0. So when k divides r minus 1, that means k divides r minus 1 means this reduces to k. This sum will reduce to k. So k divides r minus 1, this is the only possibility, that is k divides r minus 1. So in that case r becomes 1. So that is k times, here this will be k, this term will be k, and here this will become r will become 1 because r minus 1 is 0. So r will become 1. So that way this will become k times chi of 1. And what is that? And that what is chi of 1? Chi of 1 is only one term will be remaining for the case r. So that in that case chi of 1 is actually 1. So k, we will get the answer k. So since the last sum over m is a geometric sum which vanishes unless r equal to 1. Thus we have proved the result. Hope you have understood the result. If you have any doubt, you can ask me. Thank you for your patient listening.